Supercomputers and AI unlock secret materials for next-general carbon capture. Metal Organic Framework, MOF, materials can be used in many different applications, from catalysts to energy converters. Generative AI techniques, machine learning, and simulations give researchers new opportunities to identify environmentally friendly metal organic framework materials. Carbon capture is a critical technology in reducing greenhouse gas emissions from power plants and other industrial facilities. But a suitable material for effective carbon capture at low cost has yet to be found. One candidate is metal organic frameworks, or MOFs. This porous material can selectively absorb carbon dioxide. The complexity of MOF configurations. MOFs have three kinds of building blocks in their molecules: inorganic nodes, and organic linkers. These can be arranged in different relative positions and configurations. As a result, there are countless potential MOF configurations for scientists to design and test. A new era of MOF design. The team's approach could ultimately allow scientists to synthesize just the very best MOF contenders. People have been thinking about MOFs for at least 2 decades, said Argonne computational scientist Eliu Huerta, who helped lead the study. The traditional methods have typically involved experimental synthesis and computational modeling with molecular dynamics simulations. But trying to survey the vast MOF landscape in this way is just impractical. Even more advanced computing will soon be available for the team to employ. With the power of the ALCF's Aurora exascale supercomputer, scientists could survey billions of MOF candidates at once, including many that have never even been proposed before. What's more, the team is taking chemical inspiration from past work on molecular design to discover new ways in which the different building blocks of a MOF could fit together. We wanted to add new flavors to the MOFs that we were designing, Huerta said. We needed new ingredients for the AI recipe. The team's algorithm can make improvements to MOFs for carbon capture by learning chemistry from biophysics, physiology, and physical chemistry experimental datasets that have not been considered for MOF design before. To Huerta, looking beyond traditional approaches holds the promise of a transformative MOF material, one that could be good at carbon capture, cost-effective and easy to produce. We are now connecting generative AI, high-throughput screening, molecular dynamics and Monte Carlo simulations into a standalone workflow, Huerta said. This workflow incorporates online learning using past experimental and computational research to accelerate and improve the precision of AI to create new MOFs. The atom-by-atom approach to MOF design enabled by AI will allow scientists to have what Argonne's senior scientist and Data Science and Learning Division Director Ian Foster called a wider lens on these kinds of porous structures. Work is being done so that, for the new AI-assembled MOFs that are being predicted, we incorporate insights from autonomous labs to experimentally validate their ability to be synthesized and capacity to capture carbon, Foster said. With the model fine-tuned, our predictions are just going to get better and better.